Hello everyone, this is the video lecture of section 8.1 second part out of two parts, second and last part. Okay, so we introduced the concept of limit of sequence last time and a few examples. Today, the second part, we want to study a very important mathematical tool called mathematical induction. I have to lower the line over there. Okay. All right. So first of all, let's define increasing and decreasing. So a sequence is called increasing. I'm using, pointing up arrow for increasing. There are a few different ways to define what it means by increasing sequence. For example, for all n and n is larger, index gets larger than. From left to right, increasing. That could be very good definition. But there's another way of defining using in the spirit of mathematical induction. That is, if and only if an is always less than an plus 1. For all n, 1, 2. Always my next term is larger than me. So for a1, a2 is larger than a1. For a2, a3 is larger than a2. For a3, a4 is larger than a3, right? And so on. So it'll make larger index will give bigger value than smaller index, right? So you can define this way. Likewise, a sequence is called decreasing if and only if the other way around. For all n, right? Now, a sequence is called monotonic. Monotonic. If and only if your sequence is either increasing or decreasing. One, both cases are called monotonic. The increasing sequence is monotonic sequence. Decreasing sequence is also monotonic sequence. And then a sequence is bounded above. Okay, here, BDD stands for bounded. Okay? Bounded. BDD stands for bounded. Bounded above. Yeah, bounded above. There is a ceiling in the value of the sequence. If and only if there exists some real number R. Since there's some real number R, there exists. You remember this notation. There exists. This is for all. This capital E flipped. There exists. Stands for this. There exists real number n. M belongs to the set of all real number, which means a real number m. Such that S dot T dot means such that an is less than or equal to m for all n. Okay? So this is called upper bound, right? All the terms is less than or equal to m. Upper bound. Okay, when you have an upper bound, your sequence is called bounded above. Likewise, a sequence is called bounded below. If and only if there exists some real number, lowercase m, such that all sequence, all elements is greater than or equal to m. Okay, bounded below. Now, sequence is called bounded. If and if your sequence is bounded above and bounded below. So your sequence has both upper bound and lower bound, both. So they are bounded. So let's some examples. N equals n squared. 1, 4, 9, 16, 25, 36. Increasing, right? So this is increasing sequence, obviously. And 1 is the smallest value. So every term is greater than or equal to 1. Or you could say greater than negative 3. Any number less than or equal to 1 can be used as lower bound, right? So anyway, bounded below, okay? But not bounded above, obviously. But not bounded above, obviously, because it can be as large as you want. On the other hand, sequence minus -1, -2, -3, -4, the largest value is -1. Any value greater than or equal to -1, like 0 or 5 or square root of 2, can be used as an upper bound. Right? This is decreasing sequence bounded above, but not bounded below. Therefore, they are not bounded sequence. What about n plus 1? So this is 1/2, 2/3, 3/4, 4/5. This is increasing, right? Must be increasing. Greater than or equal to 1/2, all the terms, right? At least it's greater than 0, positive, right? Greater than or equal to 0, so bounded below. And this will never be equal. See, your numerator is smaller than denominator, that means it's less than 1. So 1 is your upper bound. So you have upper bound and lower bound. Everything is between 0 and 1, bounded. Because it is bounded above and bounded below, it is bounded. Okay? Because your AN is always in between 0 and 1. Okay? Now, there is a very important theorem called monotonic sequence theorem. So, monotonic sequence theorem says that every bounded monotonic sequence is convergent. Convergent means it has a limit. So every bounded monotonic sequence will have a limit. It's a finite real number, obviously. So bounded monotonic sequence. What does it mean by monotonic bounded? For example, increasing sequence but bounded. Increasing sequence is already has a lower bound. Your first one is the smallest, right? So your increasing sequence means that automatically you're bounded below, obviously. So that means increasing sequence to be bounded, hence it has to be bounded above 2. So that means increasing sequence, increasing and bounded above. Because increasing sequence is automatically bounded below, or decreasing sequence bounded below. Decreasing sequence obviously is upper bound, the first term. So decreasing sequence and bounded below. That's bounded monotonic sequence. It's one of these two, right? So each case always has a limit, convergent. in real number. You don't have this theorem if you consider sequencing rational number system. Okay. You can make a sequence out of rational sequence, bound monotony, yet limit does not exist in rational number system. So this is an important property of real number system. Basically, this one means that there is no hole. In rational number system, I can make a sequence out of the rational number, which is converging to, let's say, square root of 2. It is bounded, monotonic, increasing toward something. Yet the limit, square root of 2, is supposed to be the limit value, is not in the rational number system, even though all the sequence elements are made of rational number. That means rational number on a real line has so many holes, right? Real number system does not have a hole. So your real line is all solid line, no holes. Completeness. This is what we mean by completeness. This is the final axiom or postulate for real number system beyond rational number. Rational number, real number share so many properties, like commutative property addition, associative property multiplication, existence of identity addition of addition, identity of multiplication, blah blah blah. One difference is this completeness. Sometimes we call it completeness theorem of real number. And this is a very advanced topic. So there are many different versions of this. If you choose one of them as an axiom, the other will be derived as a theorem. You could consider this as an axiom, postulate, and then prove something else as a theorem. Obviously, in this level, we'll accept it. Okay? And intuitively, this is kind of obvious, right? Something is keep increasing. Something is increasing. And we know that there is an upper bound, bounded above. So, increasing yet there is a ceiling, then it must be approaching some value. All right? It must be approaching some value. If it is not allowed to go forever, if there's already a ceiling, either to this ceiling or somewhere below, it's going to be accumulating, right? The value it is approaching will be the limit of the sequence. Same thing for the decreasing sequence bounded below. All right. Now let's do principle of mathematical induction. Mathematical induction. In short, I'm going to call it PMI, Principle of Mathematical Induction. Let's say Pn be a statement depending on an integer, depending on n. For all n set of natural numbers, which means 1, 2, 3. This capital N means the set of all natural numbers. Okay? So your statement somehow, depending on your choice of your integer. Okay? So P1 is a separate statement from P2 or P3. So you have a P1 statement, P2 statement, P3 statement, P4, P5. All right? Somehow, these P1, P2, P3, P4 are related. Suppose that, first, somehow we can show that P1 is true statement. P1 is true. Second, if PK somehow any K statement is true, then somehow from the relations among those statements, okay, PK plus 1 is true for any K. Okay? Somehow they have among these statements, depending on different integers, have a relation there. If the previous statement is true, then it dictates the next statement to be true. All right? So, for all integers, positive integers 1. So this means if P1 is true, then P2 must be true. We don't know yet. If P2 is true, then P3 must be true. K equals 3. If P3 is true, then P4 must be true. Right? Somehow they have a relation that if the previous statement is true, then it forces the next statement to be true. If this structure of the statements, depending on the integer n, positive integer n, has that kind of relationship, and if we know that first statement is true, then you can keep, this is looping. Okay, we found that P1 is true, according to this second condition. Because P1 is true according to this second statement, because if P1 is true, then P2 must be true. Therefore, P2 is true. Because P2 is true, P3 must be true. Now, K equals 3. Because P3 is true, we just said. Therefore, P4 must be true. Now, using K equals 4. Because we just said that P4 is true, P5 must be true. What do you see? It keeps going forever. It's like a domino. If P1 is falling, then P2 falls, and then P3 falls, just like a domino. All right? Unless you touch the first block, it's going to be just staying there, right? We don't know. Unless we know the first thing is true, we don't know whether they are true or not. But if you know the first statement is true, if you tip the first block, then the whole blocks will fall. Everything will be true. So we can conclude that then all statement is true. If you can show these two. This is what we call PMI, Principle of Mathematical Induction. Okay? So, let me give you one more example. Let's say the whole California State University at Bakersfield, all CSB students, let's say, lined up in a stadium. Okay? That's the baseball stadium. All 10,000 students all lined up. Okay? Winding, but in a line. Okay? There is a first student, second student. You can give a number, spot number. First student, second student, third student, all the way to, let's say, 10,000 students. And all these students pledge or sign the contract, whatever, which says that if the person in front, they are all in a line, if the person in front of me, let's say, donate $10 to Cancer Research Foundation, then I will donate $10 to the foundation too. Everybody legally bind themselves somehow. Everybody agrees that if the person in front of me donates $10 to the foundation, Cancer Research Foundation, I will do it too. Everybody sign the pledge. Okay? Now, does it mean that you donate $10? Not necessarily. Unless the person in front of me donates $10, I am free to do whatever. I could donate or I might not donate. I'm okay. I don't break any pledge, right? But what if the very first statement suddenly says that here's my $10 goes to the foundation? Suddenly, the first statement. donate $10 to Cancer Research Foundation. Then what happened? According to the pledge, the second student, the first student is the student in front of me. That person donated $10, so I am forced to donate $10. Once the second student donates $10, third student, the second student is the person in front of you, right? Donate $10, therefore I have to donate $10. Therefore, fourth students also have to donate $10, just like domino. So you know that everyone will donate $10. That's exactly this. If everybody pledges, all K, everybody pledges that if the person in front of me donates $10, then the next person will donate $10. Everybody signed on that pledge. And then first person suddenly donates $10. Then we know that everybody will donate $10. This is principle of mathematical induction, PMI. Okay? So we're going to do 2 examples. Each of them are rather long. Application of PMI. Example 9. Consider the sequence AN defined by the following recurrence relation, which is A1 equals 2, 1/2 AN plus 6. Recurrence relation, we learned one of 2 ways to define sequence. First one is AN equals like n squared minus 3n plus 1. Explicit formula, right? Then for every term, you can calculate it right away. That's explicit expression or functional expression. Or you just give you relations among immediate terms. This is obvious for all n, right? And by having first term, you can define A2. If you know A2, you can get A3, right? So for example, let's give you an example. So this is 2, and then ANs are 2, plugging in 2. 2 plus 4 over 2, 4. Now, A2 equals 4, 5, right? Now, A3, A4 equals 1/2 A3 plus 6, 5 plus 11 over 2, right? Now, what about A1, 2, 3, 4, 5? What about A5? A4 equals, this one is 12. 23 over 2, 23 over 4, right? So you can generate this. This is 5.5, this is 5.75. Seem to be increasing, but not crazily increasing. Okay? Now, for this one, by induction, use PMI, show that AN is always less than 6 for all n. Okay? Bounded above. B. So you can use this way, but sometimes they write it this way. By induction. To show that the sequence AN is increasing. So use principle of mathematical induction to show this. Or by induction, show that this. It's the same thing, right? In short, sometimes we say by induction, means by using principle of mathematical induction. Okay? Now, if you show these two, what does it mean? increasing sequence bounded above. That means it is monotonic sequence bounding. According to the previous theorem, monotonic sequence theorem, we know that this must be convergent. So, third, find the limit of an. Now that this is convergent. Okay. Solution A. Now we have to show that, okay, this is our Pn, nth statement. That is, nth term is less than 6. Okay? So we want to apply PMI to this statement, Pn. Alright? So, obviously, what is P1? P1 is A1. A1 is 2, obviously less than 6. Right? Obviously, which means we just show that P1 is true. We have to establish these two, right? The first one is obviously easy. Checking this one. The first one. Second, now we have to establish this. Right? We have to show that this statement is true. So, how do you prove that this statement, if pk is true, then pk plus 1 is true? In order to prove this conditional statement, we have to do starting by saying, suppose that pk is true, then from the relations among between pk and pk plus 1, pk plus 1 must be true too. Right? That's what we have to establish to prove this conditional statement. That's how you prove conditional statement. Suppose the hypothesis is satisfied. Then using mathematical logic and known theorems, you just derive that the conclusion part is also true. So we're starting by suppose that AK is less than 6. That means i.e. that is we are supposing that suppose that pk is true. That's what we are doing, right? Now, this inside parenthesis just for your reference in the beginning to match what you're doing with this PMI structure. Okay? Okay. Then we need to say that, okay, from there I want to say that AK plus 1 is also less than 6. We want to conclude this, i.e. when we assume that pk is true, k statement is true, k plus first statement is also true. Pk plus 1 is also true. Now we want to derive this from this assumption using this recurrence relation. This is binding the consecutive terms, right? So, in order to create AK plus 1 from AK, what do you have to do? You have to add 6 and then divide by 2. So I'm going to add 6 to both sides. If it is true, then this must be true also, adding 6 to both sides, right? And if it is true, you can multiply by 1/2 positive number without changing the direction. So 1/2 times taking, right? Multiplying both sides of inequality by this positive number. Then we keep the same direction in inequality. And what is this? That is precisely AK plus 1. This one is 6. Indeed, we can derive this if we assume this. Okay? If we assume that if pk is true, then pk plus 1 must be true. But we know that A1, P1 is already true. Therefore, all Pn must be true. Alright? See? That's how we use Pn. So you can conclude. Okay? Therefore, AK plus 1 therefore I PK plus 1 is true. So you can conclude by 1, 2, and PMI. By 1, 2, and PMI, now you can say that Pn is always less than 6, or Pn is true for all n. Okay? Not R. Set of all natural numbers. Okay? This is a very typical way of using principle of mathematical induction. Let's do the next one. B. Okay, now this one is slightly different. Okay. A is increasing. We want to write this one as some kind of Pn structure, nth statement structure. Well, how do we apply PMI? Then we have to write this one as a bunch of statements. P1, P2, P3, P4. Well, that's why you learn the new definition of increasing function. So we have to prove that. What was the definition we just learned this session? An is always less than 80 plus 1 for all n. This is our nth statement here. All right? So that version of definition of increasing function was designed to use PMI, okay, in various proofs. So, first, consider A1 equals 2, A2 equals 4. Indeed, A2 is greater than A1. And this IE, the first statement is true, right? Now we have to do the induction part. We call it induction step. This one is called induction step. So, suppose that PK is true. K's statement is true, which means AK is less than AK plus 1. Okay? I.e., suppose that PK is true. All right, by the way, this logic works for all K, right? It does not depend on specific value of K. So we just prove this one for all K, obviously. So here, for any positive integer K, let's say this is true. Now, from there, we want to say that this is K plus 1. So when n equals K plus 1, this is K plus 2, right? So we want to derive this from here. Again, using this recurrence relation. So, how do we get from here to here? Well, just like before, add 6 to both sides. Then we still keep the already same direction. And then take 1/2 of both sides. Multiply both sides by a positive number, 1/2. That is precisely K plus 1. This is K plus 2. Next time, right? So, K plus 1 is true for all integer. This logic, this flow of idea does not depend on any specific value of K. It is true for any integer of integer K. So the second step is done. Induction step is done. Therefore, by 1, 2, and PMI, principle of mathematical induction, we can say that Pn is true. That means all terms satisfy this for all n, i.e., your sequence an is increasing. Okay? Now, as I said in the beginning, because an is increasing and bounded above, so it is bounded and monotonic. Right? Because increasing sequence is already bounded below. A1 is the lower bound, a lower bound. Bounded above, bounded below, so it's bounded, right? By A and B. By monotonic sequence theorem, limit of an, I'm going to call it L, exists. See? Convergent means limit exists. Okay? By monotonic sequence theorem. So, let's find the limit value. Now, note, what if you take an plus 1? What do you think? If limit of an equals L, as n grows, A100, A200, A300, million, billion, it approaches L. What is an plus 1? A101, 201, million plus 1. This one is just one step ahead of this. If you think about, if you draw this graph of sequence, right? So if an approaches L, even if you're one step ahead, it will be approaching the same value, obviously. This is just going through the same list of numbers in the same sequence, right? So obviously this one approaches L. Well, an plus 2, same thing, approaches L. N plus 100, yeah, approaches same value. It's just in the same list of the numbers. You go through maybe a few steps ahead, few steps behind, doesn't matter. As n goes to infinity, right? It approaches L. So we take limit of both sides of this. Limit of an plus 1 equals limit of 1/2 of an plus 6. Now, this one, in the limit property, you can take out 1/2, right? You remember? Limit property. And limit can be split over addition. Plus limit of constant sequence. Okay, let's try it. It's 1/2 of, okay. Now, these two are equal. What is this? Again, this is L equals 1/2 of limit of an, L plus 6. So L equals 1/2 of L plus 3. Oh, or I just multiply both sides by 2. 2L equals L plus 6. L equals 6. So this one is 6. In the example, 5.5, 5.75. Yeah, it was really approaching 6. Okay? All right. That was an interesting application of PMI. PMI is very useful in a lot of proof involved in sequence and series when they are given recurrence relation. Let's do example 10, which will be the last example of this section. Example 10. Consider the sequence an defined by a1 equals 1 and an plus 1 equals 1/4 minus an. Then show that I don't even say use whatever. Show that AN is bounded between 0 and 1 for all n. And then show that AN is decreasing. And decreasing in bounded. Again, bounded monotonic sequence theorem must be convergent sequence. So finally, okay? All right. Then if you, so A1 equals 1. If you're plugging in 1, you get 1/3. If you're plugging in 1/3, what is it? Multiply by 3 and 3. 3 over 12 minus 1 is 11. Right? Okay. It's hard to see a pattern out of the first few terms. That's okay. All right. Okay, let's do that. First. Now, this is our Pn, nth state. So first, we have to show that P1 is true. Well, what is A1? A1 equals 1. 1 is obviously less than or equal to 1, greater than 0. The first thing is true. P1 is true. Okay, no problem. To do induction step, second one. Suppose that Pk is true, which means your Ak is between 0 and 1. Supposing that Pk is true. Okay? Now from there we have to make Ak plus 1 is also between 0 and 1, right? Just like before, we're going to use this recurrence relation. So in order to get the next term, first of all, you have to multiply -1 to AN. So multiply -1, negative AN, -1. Then you have to flip the inequality because you multiply by negative. And then you have to add 4. 4, adding 4. Right? So these are all positive numbers because everything is really equal to 3. Now, and then you have to take reciprocal. If you take reciprocal, this is K. If you take reciprocal, then the direction of inequality will be switched, right? Because larger denominator means smaller number, right? 1 over larger number will be smaller. Because this is larger than 3, 1 over that will be smaller than 1 over 3. So indeed, that is exactly Ak plus 1. All right? Now, so that means 1/4 is, well, we proved that this is actually between 1/4 and 1/3. But anyway, this is more than enough to say that indeed Ak plus 1 is between 0 and 1. We proved much stronger one, but that's okay, right? This is all we need. We did more than we need to do. So, i.e., when we assume Pk is true, then Pk plus 1 is also true. Okay? All right. Then you can conclude. Here. You can conclude that. Okay. By 1, 2, and PMI, indeed your an is between 0 and 1 for all natural numbers. How do we prove decreasing? Just like the increasing case, we want to prove that an is greater than an plus 1 for all positive integer n. And this is our Pn. So first, we want to show that a1 is greater than a2. a1 equals 1, a2 equals 1/3. Indeed, that satisfies. i.e., P1 is true. We established the first one. Now, second one. Suppose that K statement is true, which means AK is greater than AK plus 1. Okay? i.e., we're supposing that PK is true. Right? Then, from there, we want to establish that AK plus 1 also greater than AK plus 2. Next statement is true. Alright? So, let's do that. Again, we have to go through this. Minus AK, just like we did here, is less than minus AK plus 1. Multiplying both sides of inequality by a negative number, flip the direction. And then adding 4. Okay? Now, this is actually true. You have to be careful. We want to say this. Right? We want to say that when you take reciprocal, then this one changes the direction. Because smaller denominator means larger. Now, this one seems obvious, true. Well, if both of them are positive or both of them are negative, then they are true. But what if you have a minus 2 versus 3? Does it make flip? No. When one is negative and one is positive, even after flip, you stay the same. Right? However, if both are positive, yes, reciprocal has opposite direction. Or both are negative, negative 1/4 is greater than negative 1/2. Right? So, we have to show that they are both positive. Now here, because all terms between 0 and 1, 4 minus some number between 0 and 1 will be anyway greater than equal to 3, but at least it is positive because of result of A. Because A is only between 0 and 1. 4 plus a number 0 point something will be 3 point something. Anyway, this is positive. Because they are both positive, therefore, when you take reciprocal, you have to flip the direction of inequality. Alright? This is important. So that's why I prove this bounding is first before you do this. Unfortunately, your textbook try to prove this one first before you do this. Something similar problem. And that is wrong, because in that case, you cannot argue that this is always positive. Right? Okay, so be careful when you do one of the homework problems, which is a very similar structure. Anyway, so you got it. Which means AK plus 1 is greater than AK plus 2. That means, i.e., PK plus 1 is true. When we assume that PK is true. For any K, no restriction on K value. For all K. Therefore, by 1, 2, and PMI, AN is indeed greater than AN plus 1 for all M, which means AN is decreasing sequence. Just like the previous case, by A, B, and monotonic sequence theorem, your limit of an exists. Because we just showed that our sequence is decreasing monotonic and bounded. Monotonic sequence theorem says that such sequence always convergent, which means limit exists. Okay? So, just like the previous, so we just take the limit of both sides. An plus 1 equals limit, n goes to infinity, 4 minus an. Now, this one, 1 over limit of n goes to infinity of 4 minus an. We know that from this, because this is true for all n, that means our L must be between, where did it go? Between 0 and 1. Okay, let me check the recording and find the cat. Here, L is greater than or equal to 0, less than or equal to 1. Even though an is always positive, the limit could be still 0. Think about 1 over n. 1 over 2, 1 over 3, 1 over 4, 1 over 100, 1 over million. Everything is positive, yet limit could be 0, right? So anyway, we know that L should be 0 and 1. So this never be 0. That's why you can split limit over division. And this one is 1 over 4 minus limit of an. So what does it mean? L equals 1 over 4 minus L. Right? We just covered it. Limit of an plus 1 is same as limit of an both L. So multiply both sides by 4 minus L. So 4L minus L squared equals 1. Bring it over here. L squared minus 4L plus 1 equals 0. So we have to solve quadratic equation. Minus b plus minus square root of b squared minus 4ac. 4 plus minus 12. Square root of 12 is 4 times 3, so 2 square root of 3 over 2. 2 plus minus square root of 3. So 2 plus square root of 3 or 2 minus square root of 3. Your limit. But look at this. L must be somewhere between 0 and 1. This is 1.7 something, 3.7. This one, 2 minus 1.7 something, 0.3 something, 0.2 something, I don't know. So this is the one. So this will be 2 minus square root of 3. Okay? So, these last two examples are very nice application of principle of mathematical induction. And you can actually do all the homework problems related to PMI if you go through this and understand these two examples. Okay? And remember that this kind sometimes it's better to show boundings first, most of the time. Try to show bounding. Even if your homework problem asks you to show this one first. Okay? Remember that. Alright, this is the end of section 8.1. Thank you and see you next time.